So, we have come to the concluding lecture of this particular course, which is corrosion 1. Today we have lecture 41. Until now, what we have done in the last couple of lectures, we have tried to understand corrosion events of metals from consideration of by considering mixed potential theory, and we have taken 3 examples. Today we will have 2-3 more examples, and then we will conclude our session, and the rest of this there will be more on this corrosion, which will be covered in corrosion 2 later on. Now, coming to this lecture 41, we will continue our discussion on case studies and understanding the corrosion event. With the use of So, what we have done before, we have one of the case studies that a noble metal is galvanically coupled to an active metal, and we saw that because of the noble nature of that galvanic coupled material, the corrosion rate of active component increases. And then if the area of the noble metal increases without increasing the area of the active component, the corrosion rate further increases because of this enhancement in the cathodic area as compared to the anodic area. So, now in this case studies, the case studies 1, case study 1, today's case study, rather I would say case study 4. Here we will try to see the corrosion event when 2 active components are coupled, and when they are coupled, one of the components will become cathode and another component will become anodes, and then the anodic component will corrode and the cathodic component, after joining these 2 active metals, the cathodic part will get protected because of this enhanced corrosion of the anodic part. Now, let us say what I am pointing is, let us say iron and zinc, they are both corrode in HCl solution, or rather they corrode heavily when they are not joined together. Now, in case of separate situation, for example, in one beaker you have HCl where you have Fe, another beaker you have HCl and you have zinc block. Both the metals will corrode as per the explanation given with reference to mixed potential theory. If I try to draw Evans diagram for both the metals in HCl, we will have the nature of the plot will be like this. I am just drawing one after another, and this is one below another. So, log I, this is also log I, this is E volt, let us say this is E0 hydrogen equal to 0, and let us say this is E0 zinc plus zinc, which is equal to 0.76 volt. This is in case of zinc, and let us say this is for E0 H plus H2 equal to 0 in case of iron, and here it is E0 Fe plus Fe equal to minus 0.44 volt. I0 of H, simply I am writing H plus because H2, simply writing H2 because this is I0, the exchange current density of hydrogen reaction on zinc surface is here, and then I0 zinc on zinc surface at this point. Now, they will have their mixed potential. This is E core and this is I core of zinc, and at this point I C equal to I A. Similarly, in case of iron, generally the exchange current density of hydrogen evolution reaction is higher. So, this is I0 of hydrogen reaction on iron surface, and it is almost on the similar level. This is I0 iron on iron surface. They will have their own mixed potential. When they are dipped separately, this case and this case. So, this is in case of this, at this point, this is the point of I core, this is E core, and here we have I C equal to I A or I A equal to I C. So, at this point we have no net current, but the iron corrodes at a rate of I A, which is equal to I core. Now, interestingly, if you see generally, if you are plotting it on the same marking or the same values, I see that this corrosion rate of iron in HCl is little more than the zinc, but zinc E0 is lower than E0 of iron. Now, we have to join them. So, now this is iron, this is zinc. Now, we are putting it in HCl of the same concentration. Now, what happens? That case, you see, in separately this is also active, this is also active, and the cathodic reactions here is H2, and similar reaction, cathodic reaction is happening here. So, both the cathodic reactions are here, and here the anodic reaction is, and here it is zinc plus plus. But when they are connected galvanically, then what happens to this Evans diagram? That will tell us which one would corrode more and which one would corrode less. Now, if I combine them, this is E0 zinc minus 0.76 volt, this is E volt. Let us say this is E0 plus Fe equal to 0.44, which is minus volt, and this point is E0 H plus H2 equal to 0. Now, this point lies here, this point lies here. So, now if I I0H2 on zinc, this is I0 zinc on zinc. I will shift this point a little bit so that this is the point. Now, if this is my point for iron, which is basically the E0 point, let us say it is here, this is I0 H2 on iron surface, this is I0 Fe on Fe surface. So, they meet at this point. So, I put it in a different color. This is the point which is I0 for hydrogen reaction on iron surface. Now, I am just marking those potential points or the E0 points for individual half cells reaction. As we have known from mixed potential theory that during polarization, whenever a reaction, whether it is a cathodic or anodic polarization, experiences another reduction reaction or oxidation reaction, they should be clubbed or they should be joined or they should be added in order to reach to the mixed potential where the net current density should be 0 or total cathodic current density is equal to the total anodic current density. Now, this is hydrogen evolution reaction and polarization, cathodic polarization for hydrogen reaction on zinc surface, and this is the second hydrogen evolution reaction on iron surface. So, these are two cathodic polarization lines, and then at each potential we have to add up those two current densities corresponding to these two polarization plots, and then we have to get a new polarization line. So, this is, let us say, this color I am putting blue green color. So, this becomes my line which corresponds to IC equal to IC1 plus IC2. So, that means this is for this one and this is for this one at each potential. For example, if I consider this potential, then this point indicates current density IC at this point and IC at this point. So, this IC is equal to, let us say this is A, this is B. So, IC A plus IC B, that is what this line has been drawn. Similarly, when this polarization line is extending, once it reaches to this potential, then again it is experiencing one more anodic reaction, which is, let us say this one I am putting as 3. So, and this was 4. So, 4 and 3, they are two anodic reactions, and when this 4 is reaching to the polarized value of this potential, then it is experiencing iron oxidation reaction, which is also polarizing. So, from there if we continue this line, then here we have to add that part also. So, if I add it again with a green color or let us say blue color. So, this is the added part. This line, this black line is the polarization line for zinc, and this blue line is the polarization line for iron polarization or anodic iron polarization plus zinc polarization, and here both are anodic, and at any point, let us say if I consider this potential, at that potential, let us say if I consider this potential and this value, let us say I A K, and this particular current density, let us say I A P. So, here this is I A total and this one is I C total also, this one also I C total equal to I A K plus I A P. This is for iron, this is for zinc. So, now we could see that this line, this one and this one, these two, wherever they are meeting, that point indicates the new mixed potential where I C total is equal to I A total. So, this is the point where they are meeting. Now, at this point, I C total equal to I A total when they are combined. So, this plot is basically when they are clubbed, they are joined. Iron and zinc are forming galvanic couple. So, at this particular point, let us see what are the current densities of iron corrosion, iron current density for the anodic reaction of iron and a current density corresponding to anodic reaction for zinc. That can be easily found out. Since this is my new E core and this point is also I core. Now, if I draw a line the line, this becomes my E core and then this point is basically I C for hydrogen evolution on iron surface, and this point is equal to I C of hydrogen on zinc surface. Similarly, since this particular 2 points, this particular point is cutting the cutting this particular line, and here it is cutting the black line corresponding to this line. So, that is what they are our two current densities for cathodic polarization. And similarly, this point is cutting on the zinc anodic polarization line. So, this is IA zinc, and here also it is cutting the iron polarization line. So, this becomes IA of iron. So, now if we combine them, so this combination of this and combination of this, that would lead to the condition which is IC total equal to IA total. Now, interestingly, in the beginning when they were not connected, they were separately immersed in HCl solution, we could see that the iron corrosion rate was this one. So, this point is E core for iron, and this point is also I core for iron before joining. So, now after joining, the corrosion rate of iron has reduced from this value to this value. So, that means the corrosion rate of iron has reduced when they are joined together. And what happens to the corrosion rate of zinc? The corrosion rate of zinc has actually increased when they are combined. The corrosion rate of zinc was at this point, this is I core zinc when they were uncoupled, and this was the value E core when they were uncoupled. But after coupling, I could see that the corrosion rate of zinc has gone to, so the corrosion rate and this value at this point, the IA is much higher than the IA what used to be here before coupling. So, the corrosion rate of zinc has increased. So, now interestingly, one more information: before coupling, the corrosion rate, the IC of hydrogen evolution reaction on zinc surface was at this point, and after coupling I could see that hydrogen evolution reaction rate or IC on zinc surface has gone to this at this point. So, I could see that corrosion rate of the not corrosion rate, the cathodic current density for the hydrogen evolution reaction has moved from this point to this point. So, the rate of hydrogen evolution has gone down, has decreased rather, on zinc surface, whereas if I could see the what happens to the corrosion, what happens to the rate of hydrogen evolution on iron surface, the iron surface, it is here, the hydrogen evolution rate or IC on iron surface is at this point, and before coupling, hydrogen evolution rate or IC on iron surface was at this point. So, I could see that the rate of hydrogen evolution has increased on iron surface. This is important observation. That means the hydrogen evolution or the hydrogen reaction on zinc surface has gone down or has decreased, whereas hydrogen evolution on the iron surface has increased. Or in other ways, since hydrogen evolution is the cathodic reaction that is taking place on both the surfaces, I could see that the hydrogen evolution or the cathodic reaction is preferably taking place on iron surface rather than zinc surface. And from the zinc surface, I could see that the corrosion rate of zinc has increased, whereas the corrosion rate of iron has decreased because of this coupling. So, as we have understood before that if we have preferable cathodic reaction on a surface, that surface becomes cathode, and if we have preferably anodic reaction on some surface, that surface becomes cathode. So, here iron turns out to be cathode area, since preferably hydrogen evolution takes place on that and iron dissolution or the anodic reaction for iron has decreased to a great extent. Remember, this is in log scale, log I scale, that means that decrease is quite a lot, because it could be of the order of 10 to the power 2 to 3 order scale. So, the cathode area, so iron becomes cathode, and since zinc surface rate of hydrogen evolution has decreased, that means the cathodic reaction is less on zinc surface. So, and zinc dissolution has increased on the zinc surface. So, this becomes zinc becomes anodic area, or it will act as anode. Exactly the similar situation happens when we have iron face, this is iron, and on top of it if I put a zinc layer, this is the red color is the zinc layer. So, until and unless zinc is covering iron surface, we have one single reaction, which is zinc dissolution. But the effect of zinc on the iron corrosion will take place whenever there is a opening. Let us say this is the opening part. Now, this opening region is basically iron, this is iron, and rest of this case is zinc. Now, zinc would act as anode and iron would act as cathode, and in the environment this reaction would take place, since the environment is nearly neutral, and this reaction would take place on cathode, since iron acts as cathode, and the anodic reaction would take place on zinc. So, where zinc. So, zinc dissolves and iron is protected because of this mechanism, and that mechanism can be easily understood from this diagram, which is the Evans diagram for the combined situation. This particular method of protecting iron surface, we call it sacrificial anode. In the zinc becomes sacrificial anode, and this is called sacrificial cathodic protection. Since by using sacrificial anode we are creating that iron surface as cathode, and then it is basically the zinc is sacrificing itself in order to protect iron. We call this particular method as galvanization. Galvanization is nothing but the putting zinc plating or zinc coating on iron surface. This, since we have talked about sacrificial protection method, so there are cathodic protection, we call it cathodic protection. And this cathodic protection works on the basis of sending negative current to the cathode. Let us say if we have this E versus log I, and if this is I0 for cathodic reaction, let us say this is the cathodic polarization, this is anodic polarization, this is iron, and this is the potential which is the new potential or new mixed potential, and this is the I core, and these are corresponding E0 values of 1 and 2. Now, how can I decrease in corrosion rate? If I need to decrease, I need to decrease IA, and this particular line is IA and this is IC. Now, in order to do that, if I go downwards, now this is my new starting point corresponding to over voltage is 0. Now, as we go down, that means if I put neta to be negative, then I will go down. Let us see if I reach to this potential, I could see, and let me draw the corresponding two other lines. For this case it is cathodic polarization, this case it is anodic polarization, but since these potentials are extreme, so this new potential would arrive in between two potentials. So, now this particular point is, let us say, IC prime, and this particular point is IA prime, and if I keep this potential at this potential with this over negative over voltage or the cathodic over voltage, I could see that the corrosion rate which was initially here before polarization, I can reach to the new current density of that iron dissolution at this point. Okay. So, it is decrease in corrosion rate of iron, and interestingly during that I am sending this extra negative current, and then I applied is nothing but IC minus IA, and here IC is greater than IA. So, that is the philosophy of cathodic protection, and you can do it by using sacrificial anode by zinc, or you can have it by sending negative current to the iron structure which is to be protected cathodically from a DC power source. It is DC because we have to keep this iron surface to be cathode all the time. Now, in case of this, in case of sacrificial anode case, so if we have, this is a soil, this is a soil, below the soil we have iron piece and zinc piece, they need to be connected. I can connect them, and then leave it like this. So, in that case, in this becomes my electrolyte, this becomes my anode, this becomes my cathode, as discussed before, and the current IC will go from this to this, because if it becomes cathode in case of galvanic corrosion, this becomes positive terminal, this becomes negative terminal. So, the current which is I flows negative to the electron flow. So, IC is going this way, and it means electron is coming from this end to this end, electron flow, and once electron comes here. So, these electrons will be consumed for cathodic reaction. So, CR is cathodic reaction, and the electron would be supplied by dissolution of zinc, and the current, this current will flow from this direction. So, it will flow through this to this and then coming back like this. So, whenever the current enters into electrolyte from a metal, that zone is the corrosion prone zone, and whenever current enters into a metal object, that part is protected. So, that is what this part is protected. Like that way, current will flow like this all the time, and then the entire surface of the metal is protected, and by that time, during that time, zinc surface is actually corroding. So, this is sacrificial anode. So, another situation I could have where I have an iron piece, and this is a auxiliary anode, this is auxiliary anode, which does not take part in any reaction, rather the anodic reactions take place on this auxiliary anode. So, now if I connect it to external, this is in below the soil, and if I connect this end with a DC power source. So, the and this is the negative terminal, this is positive terminal. So, electron is going to iron and current is flowing to this auxiliary anode. Now, since electron is coming here, so that means I am sending preferably IC to the iron surface. So, if I send IC to the preferably IC to the iron surface, that means I am going towards this, that means I am going towards the anodic cathodic polarization on the iron surface. So, this becomes cathode. So, cathodic reaction happens on those surface and iron is protected. So, this particular process is called impressed current cathodic protection. So, now you could see there are two ways to protect a metal, one by using sacrificial anode, another by using auxiliary anode by using a DC power source. And why DC power source? So, all the time this iron should be maintained as cathode. So, that is what it is DC power source. In case of AC power source, this terminal polarization changes. So, one time it becomes negative, another time it becomes positive. So, that time iron also becomes vulnerable to dissolution. Now, finally, I would just explain one more example and then we will wrap it off for this particular session. Now, as we have informed that this is case 5, let us say, previously we could see that if we have concentration polarization, let us say so, this are basically I max value, I max 1, I max 2, I max 3, and we have seen that with increase in velocity. So, this is if I increase velocity, I could see that the I max increases, velocity increases, I max increases. Now, if we have two metals, in one metal we have the polarization behavior is like this, another case the polarization behavior is like this. So, that means in two cases I would have different corrosion rate situation, corrosion rate variation with velocity. Now, you could see in this case of metal 1, this is metal 1 and this is metal 2, and this is the polarization, this is the corrosion potential and corrosion rate for metal 1. So, this is I core M1 and this is E core metal 1, and whereas in case of metal 2, I am just drawing the other lines, cathodic as well as anodic polarization line. In this case, I could see when the velocity is this much V1, let us say corresponding to V1, this is V2, this is V3. When it is V1, I could see that it is cutting at this point. Since that time this is the point where IA equal to IC. Now, if we increase the velocity, the new mixed potential is at this point where again IA equal to IC. Now, if we increase velocity further at this particular V3, but I could see that it is not cutting in that concentration polarization region. I am cutting the potential, this cathodic potential, cathodic polarization line at this point where again IC equal to IA, and IA is nothing but the corrosion rate. So, if I plot in case of two metal, this is corrosion rate, let us say I plot corrosion rate. In case of metal 1, whether it is V1, V2 or V3 does not matter, because it is cutting all the time on the activation polarization part of that cathodic polarization line. So, its corrosion rate with velocity will be a constant one, whether it is a V1, V2 or V3. Now, let us say this is V1, this is V2 and this is V3, but all the time it is the same point, same corrosion rate or I core. Now, in case of metal 2, this is metal 1. In case of metal 2, situation is little different. Now, when the velocity was V1, the corrosion rate was at this point. When the velocity is V2, the corrosion rate was at this point, and when the velocity has become V3, the corrosion rate has gone to this point. And beyond that, if I increase velocity further, it will all the time cut the cathodic polarization line at this particular point. So, it will become constant. So, now in V1 the corrosion rate is the lowest, and then or as per this diagram I could say that the corrosion rate is at this point. Now, V2 the corrosion rate has increased, and then V3 still increased, and then if we increase the velocity it will be constant. So, now the corrosion rate plot is like this. Now, in this case even if you go for V4, so it was like this. So, this is V1, V2, V3, V4, but in case of M2 the corrosion rate variation is like this, since they are cutting at different points depending on the velocity increment as well as change in Imax. So, this is another behavior that can be explained with the help of mixed potential theory. Finally, we have come to the end, and as we have seen that we could understand corrosion or the fundamentals of corrosion has got two parts. One is definitely Pobe diagram, another one is the kinetics part, one is thermodynamics, another kinetics. And in case of thermodynamics we could see that we could select areas in that potential pH axis where we could get passivity and where we could get corrosion or immune zone. We have given some examples. For example, in case of iron and aluminum, if we have a pH of around 9, in case of aluminum it dissolves, even if aluminum is considered to be highly passivating metal. But in case of iron, if we go beyond around 13 pH, again there could be a possibility of dissolution. That is what in case of concrete, the rebar, the pH is maintained around 12.5 to 13, around that level. So, that is what the iron always remains in passivated condition. But if we have aluminum there and if we increase that pH to 13, then aluminum definitely would corrode. So, that was one part. The another part is this mixed potential theory as well as its associated complications, as well as the not complication, I would say, the associated equations, and then finally how we could analyze some of the corrosion events on the basis of events diagram. Those are depicted in this particular corrosion 1. So, that is it for corrosion 1 part, and in corrosion 2, which will be taken up in future, near future I would say, where we will take up passivation. Generally passivation happens when we go for anodic polarization, or rather high anodic polarization, and we will try to understand corrosion events on the basis of passivation and mixed potential theory. We would also consider some of the practical events of corrosion like cavitation damage of impeller blades. Then we would also consider high temperature corrosion, mainly the oxidation part. So, that is it. Thank you.